morning, everybody. I would also like to thank the organizers for, well, putting me here in the first place and putting you also here in the first place, putting us all into the same room. Roberto and I were postdocs 20 years ago, and nothing has changed since. I mean, certainly we haven't changed, and the only difference is that PhD students keep getting younger and younger every year. What I'm going to do is I'll deliver introductory lectures, starting with the very basics of inference. For some of you who've been to IFERNET events before, this may be a repeat of things you've heard before, but I'll always try to put a slightly different and personal slant on it. Also, I tend to speak very fast. Right now I'm slowing down, but if I get caught up and start talking very fast and you can't understand, please do slow me down. Okay, the topic is frequentism versus Bayesianism in inference. So let's call it elements of statistical inference. What I would like to do is introduce two modes of thinking, two philosophies in statistical inference, and the names under which they run, frequentism and Bayesianism, are loaded. They are contentious and highly politicized. There's philosophies whose adherents tend to be very aggressive about their own views versus the views of other people. And this has to do with the use of these two terms in interpreting what probability means. So statistical inference is trying to find out about things in the presence of uncertainty, and probability quantifies that this uncertainty. But we don't really know what probability means. And the frequentist interpretation means probability is relative frequencies of certain events in the limit of a very large number of events. And the Bayesian interpretation means probability quantifies the degree of belief. And nobody really knows what belief or degree of belief means, but the Bayesian interpretation posits a number of axioms about probability, and these axioms define what is meant by degree of belief. Now, I'm not going to talk about these two philosophies because it only gets into arguments which I think are counterproductive and best left to philosophers. But these two names have lent themselves to two distinct schools in inference, which are only loosely tied. They're tied somewhat to these labels, frequentism and Bayesianism, but not exactly. So when I say in inference I'm a frequentist, it means something else than when I say in probability interpretation I'm a frequentist. So I'm going to start with frequentism, which does emphasize the relative frequency of events in a large sample, but there's somewhat more to it. So for instance, if a coin is tossed 100 times, a frequentist will ask, well, how many times did it come up heads and how many times did it come up tails? But there's more to it. And this is how the underlying parameters, things we're trying to learn, are treated. For instance, a coin is tossed. And we don't know whether it is a fair coin or whether somebody has put a little bit of lead right in the top layer, which tends to come down when it's tossed, so heads comes up more than tail. And a frequentist would say, here's the coin. Do I have one? I do. So here's the coin. It either has some lead in the top layer or it doesn't. I don't know about it, but that doesn't mean there's not a specified amount of lead in the top layer, none or quite a bit. So the parameter we're trying to learn is a fixed entity. We don't know what it is, we're not being told, but it exists and it's one fixed particular value. A Bayesian, on the other hand, would say, well, with a certain probability there's lead here and with a certain probability there's no lead. A frequentist would focus on the fact there is some lead or there isn't, I don't know how much, but it's something which is fixed from the beginning. And these two different views shape the tools and concepts which are used to analyze statistical data. So the basic setup is always we have a statistical model, and that statistical model produces data, let's call it X, with a certain frequency. So for a coin toss, if X would either be heads or tails, and it does so given a certain parameter, call it theta, the amount of lead in the top layer of the coin, or data is produced given a certain hypothesis. So there is lead or there is no lead. So X would be the data and theta would be a parameter. H would be a hypothesis. And all the tools we're going to use to analyze data and, for instance, try to learn the value of this parameter or try to learn whether or not the hypothesis is true is going to be based on a statistical model which tells us how data depends on parameter or several parameters and on the hypothesis. So this notation means a conditional probability. It tells us how probable X is given condition on the value of theta or condition on the hypothesis H. Am I being understood? I'm not talking too fast? Okay. Am I going too slow and am I boring you? No? Okay, everything's fine, good. You can tell me to speed up or slow down as you like. Okay, So, using these probabilities as basic tools, we're now going to, or as the entities to build our tools from, we're now going to look at some specific ideas from the frequentist toolset in order to analyze data. And I'd like to wipe the blackboard. How can I do that? Perfect. A knot. It's not for something else. That's for the blackboard. Okay. And the first concept to look at is called p-values. And the concept of p-values uses what is called a null model, a boring hypothesis, in order to ask how probable it is that we observe the data we see under a boring hypothesis. And what is the boring hypothesis? That depends on the particular problem at hand. For instance, in the case of coin tossing, the boring hypothesis would be it's a fair coin. Nobody put lead there, and we count the number of heads, and it's simply drawn from the distribution which an unbiased coin produces. So for instance, we make 20 tosses of our coin, and 15 of those come up head. If you look at these 15 heads and go, well, maybe this wasn't biased coin. I mean, 15 out of 20, that's a pretty large number. And the p-value tries to quantify that and asks, well, how probable is it to have 15 heads or maybe more if the coin indeed was unbiased, fair, without any lead in it? That would be the boring hypothesis. This probability of having at least 15 heads, that is what in frequentism is called a p-value, where p just stands for probability. And in our particular case, that is easy to calculate. Involves the binomial coefficients with n going from 15 to 20 times the probability of having a certain number of heads and tails, and if you calculate it, it comes to just about 20%, to just about 2%. Yes. What did I say? Oh, yes. Thank you.
So, Johannes, I was always confused why you were interested in the probability that x is larger or equal than 50
Right.
instead of x being equal to 50.
Right. So
Because that's my data.
that is very true. But for a moment, consider a continuous probability distribution. The probability of having your data as 1.725910 and so on and so on and so on is 0 anyway. And this is why this is very true. On the other hand, you would have been just as surprised had you had 16 or 17 or 18 hits. And this is, so there's nothing special about the 15. What is special is the 15 being so large and far away from 10. So this is why they look at the cumulative probabilities. But I agree with you, there's nothing in this which comes from above. There's nothing of this which is given to us and dependable and rigorous. It's a tool set which has been developed over time and follows certain conventions. So I would say this is a feature an approach which makes sense if you talk about, well, 16 and 17 and 18 would have surprised me as well. But had I left out this sum, I could have proceeded in the same way. The nicer thing about this is...
If it's Gaussian, it sort of makes sense, right?
Oh, it makes sense.
But if T would be some wobbly multimodal kind of distribution, it doesn't make any sense.
Well, it still makes sense if n is large. So, as I came here and observed a car with a license plate HK7592, what's the probability of this happening by chance? It's an extraordinary event. It's 1 in, I don't know, several billion. But is there anything amazing about it? No, I observed some number plate, and it happened to be HK75901, but it could have been any other number, and there's nothing special about it. And if I had tossed a coin 1,000 times, and it would have come up heads 550 times, or 551, 552, those wouldn't be very different in the level of surprise they generate. So this sum ensures a sensible limit when the discreteness in the data disappears as the number of samples gets large. But one can argue forever what it should be. There is no approach sort of handed to us from axioms or from above. It's all handmade, and in this particular case, I'd argue it makes sense, but fundamentally it's a definition. It's a small number. Should we say, oh, 2% is very low, this is probably a biased coin? Or should we say, oh, 2% isn't actually so bad, probably the coin is unbiased? And at this point, frequentism gives us no answer. It doesn't specify a level of probability here to decide between two hypotheses. But it simply quantifies how likely a certain event is under the null model. Different subjects, different research directions have fixed by convention, and at this point it really does get bad, certain levels for p-values. For instance, if you work in experimental psychology, then the magic level of p-value is 5%. I see some nods here. If you calculate a p-value, it comes out lesser than 5%, you're allowed to publish. If it comes out 6% or 7%, you're not allowed to publish. You must reject the notion that this data is in some way special and must accept the null hypothesis. If, on the other hand, you work in biomedical data and use sequence alignments in order to assess whether a particular sequence of DNA is related to some other DNA sequence, then the p-values must be 10 to the minus 9, 10 to the minus 10. And if they're not, you can't publish. There's nothing magic about these levels, and people just get used to them, and they can certainly be abused and are being abused. For instance, a shocking story is somebody analyzed p-values from different areas of research and found in those areas where 5% is at the magic level, they magically cluster just below 5%. So they always are 4%, 4.5%, never 1%, 2%, and that shouldn't be. Unless somebody is playing with these p-values and tweaking the data in order to just get to the magic 5%. So,
of course, this 2% or 5% might be not as surprising if my sample is, say, 20, n is equal to 20, but if n is equal to, say, 10,000,
yes,
then the situation might be different. No?
Absolutely. So, this number must be put in relation with the particular situation we're in, and frequentism can't do that for us, and doesn't. And in order
it does,
to...
right?
Pardon?
It does, right? If you had, instead of 15 out of 20, you had 150 out of 200, your p-value.
Oh, so this is true. You can compare p-values across different sample sizes. And this is where this sum is important, and it allows you to do that. But unless you know how frequent biased coins are, for instance, say, what's the probability that somebody actually put some lead in the coin, you can't make a statement on the probability that the coin is actually biased or that it's unbiased. And frequentism makes no statement about that. Bayesianism does, and I'll come to how it does that. Okay. Now, p-values, many subjects use them, many abuse them. There's even people arguing that p-values should not be used because they give us a false sense of security. They're bound to stay with us. The meaning is how probable is the data we observe, or particular features of the data we observe, given a boring hypothesis. It doesn't mean that the boring hypothesis is true with a certain probability or false with a certain probability. That we don't know. It just says if the boring hypothesis is true, we expect to see data as extreme as 15 heads or more extreme with this particular probability. Now the second concept, less widely used than p-values, and even less well understood even by people who practice them, is called confidence intervals. trying to learn a particular parameter, call it theta. We have a certain amount of data to do that, and we use the data not to calculate theta itself, but to calculate an interval, call it theta 1 to theta 2, and calculate the interval in such a way that it is associated with a certain confidence level. For instance, 90%, 95%, 99%. What does it mean? It means if we repeated this procedure on another data set, just like the first one, and repeated it again and again and again and again, then in 90% of the cases, or 95 or 99% of the cases, the interval would include the true value of theta. So the key thing is, the confidence interval doesn't mean the parameter theta lies within this interval with a probability of 90% or 95 or 99%, because to a frequentist, that statement doesn't even make sense. The parameter, remember the parameter is fixed, so for any interval, the parameter either lies within it or it lies outside it. But you can't associate a probability with that statement. It's a statement which is either true or false. Instead, the confidence interval is a statement about the method we used to derive the interval, and the interval was derived in such a way that if the procedure were to be repeated, then in 90% of the cases it would cover the true value. I'm willing to bet that if one took a poll amongst people who use confidence intervals and asked, look, what does it actually mean? I'd be willing to bet that a good fraction of them, with a high frequency, you would find the statement, the interval includes the true value with a certain probability, rather than the actual more complicated and convoluted statement, which is a statement about the method used to derive it, not a statement about the actual parameter. But you see here already how hard life as a frequentist is. It never makes statements about probability of the parameter. It can't do that. And instead, it makes statements about the methods and its reliability. This question. Yes. So the question is, do you need a model in order to do this? And absolutely yes. You need a model of the data to generate your repeated data type. You can't actually take the data again and again and again and again. You had the data once, but you say it comes from a certain model, and under this model, if I sample more data with a particular assumption about theta, well, in 90% of the cases, it would, the interval calculated would include the true one, and in 10% of the cases, it wouldn't. So absolutely, it's a statement about the model. It's not actually a statement about the underlying parameter. The third key concept of frequentist statistics is based on what is called the likelihood. And there's two different ways of looking at probability, because probability depends on two things. It depends on the data, and it depends on the parameters, theta. And if we look at this with a fixed parameter theta and vary the data, so as a probability, as a function of x, this quantity is called the probability. If instead we're keeping the data fixed and we vary the parameter theta, it's called the likelihood. And at this point, I admire the English language. It allows us to make this distinction. In colloquial English, probability and likelihood mean the same thing. But having two words for the same thing allows technical language to make a strict difference between this function, which depends on two things, and once you focus on one and leave the other constant, call it probability, and once you leave the other constant and vary the parameter, call that the likelihood.
Sorry, I think it's X.
Yes.
The second one is not really a probability.
Exactly, it isn't. It isn't. But it's still a function of theta. And as a function of theta, we give it a name and call it the likelihood. So it's always probability of the data, and that is a normalized probability distribution, and the likelihood of a parameter, and that isn't normalized, it's not a probability, but it's some function of theta, and traditionally it's called the likelihood. And a key way of estimating a parameter in frequentism is to vary theta and look for the maximum of theta given the fixed data. So try out different values of theta at a given value of the data and find the one which maximizes the likelihood. And again, this is not something which we can derive, or in this context, have derived from anything. It is constructed and proposed as a way to infer, to make an estimate about theta. Another way of doing this, by the way, is instead of maximizing the likelihood, we can equally well maximize the logarithm of the likelihood. That'll be the same thing because the logarithm is concave. The maxima are always going to be in the same place. Now you can ask, why this particular estimate? And I've been told by a friend who's a frequentist that it comes from confusion between the word likelihood and probability, and apparently the great statistician R. Fisher said, well, it simply maximizes the likelihood, so it's the right thing to maximize. But of course, the likelihood being distinct from the probability isn't a quantity which lends itself to maximization. So when we say, let's consider this particular estimate, we must ask, well, what are the properties of this estimate? It's not something which follows from some theory. It's something we can try, and it either works or it doesn't work, and we need to figure out whether it works, and indeed what works means in this context. So it turns out this particular estimate has a number of attractive properties. And all of these properties concern how good this estimate is if the sample size is large. And there's two properties of this estimator. And the first one runs under the name of consistency. And consistency means, suppose that the data were actually generated from our model. So we're drawing identically distributed samples, independently distributed samples from P of x given theta. So the probability and the likelihood of observing a particular set of data, x1, x2, x3, and so on, is simply a product of these probability distributions. Then, if n gets large, our estimate, according to the maximum likelihood prescription, tends to theta. There's a classic experiment of a British mathematician who was locked up as a prisoner of war in the Second World War. And he didn't have very much in order to keep himself amused, but he did have a coin and a piece of paper. And he said, I'm going to use the time I have and keep tossing this coin over and over and over and over again. And he spent several years as a prisoner of war and tossed the coin millions of times in order to experimentally determine whether or not it was a fair coin. And indeed, the estimate for the bias gradually tended towards 1/2. I need to make this statement here more precise and say what this limit actually means. And this limit means what mathematicians call convergence in probability. Namely, the probability that the estimate differs from the true underlying value by some amount epsilon or more as n goes to infinity tends to 0. And that's one way of specifying what this convergence means, and the technical word is convergence in probability. So as you make n larger, and your estimator is always going to differ a little bit from the true value, but the larger the sample size gets, the probability of a difference between theta and theta hat becomes increasingly unlikely. The second statement is what is called efficiency. And the statement is there is no consistent estimator achieving a lower mean squared error than maximum likelihood. So in a specific sense, the maximum likelihood estimator is optimum. And the sense in which it's optimum is, first of all, let's talk only about estimators which are consistent according to the consistency definition we have just used here. So if an estimator gives us an estimate which is different from the true value in an infinitely large sample, let's forget about this. Let's rule this out. We don't want such estimators. Let's only look at consistent ones. And then, in the family of all consistent estimators, all methods of deriving estimates of theta, let's compare them and ask, what is the mean squared error? So, the theta hat minus theta squared averaged over the distribution of the data, and compare these averaged squared errors among each other. And the statement is that maximum likelihood achieves a lower bound of this mean squared error, which can't be reached, which cannot be improved on. And the statement is actually a remarkable inequality. The variance of theta hat for a large number of samples, the mean of theta hat by consistency is theta. So this is just is actually just the expectation value of theta hat minus theta squared times a quantity I is greater or equal than 1. And this quantity I is something that can be calculated It's a quantity which you get from taking the first derivative of the log of the probability distribution with respect to theta, square it, and average over the data. And this beautiful inequality has a name. It's called the Havana bound, or also the information inequality. And if you ask me, it's a little bit like the Heisenberg inequality in quantum mechanics. It plays off two variances against each other. One, the variance of the estimate, and a second derivative, the square of a derivative of the probability distribution. And if you want some intuition on this quantity here, let's, for instance, look at statistical physics and assume the data is exponentially distributed with some parameter. So, for instance, probability of x given eta is 1 over z e to the minus eta e of x. If you consider just to gain some intuition on this, for a moment, this Boltzmann distribution, and you're trying to estimate the inverse temperature eta. And if you plug this probability distribution into here, you find that I is simply the variance of the energy. So it's the expectation value of E minus the mean of E under this probability distribution squared and averaged. It's, yes?
So both of these quantities, they depend on the data size, right? So variance of theta
So this
depends
is-
on n, and I also depends on n, right?
Yes?
Oh, so that's my question.
Yes.
It doesn't hold for all n.
It's, well, the key, okay. This actually, sorry, this holds for all n, but repeated, but this variance here is a repetition over a huge number of experiments. So each experiment gives you n data sets,
Right.
and if you repeated that, you would get a certain variance. And if you had,
Which depends on n.
which does depend on n, if your estimator is consistent at, sort of is finite n consistent, then you get this here. If it's inconsistent at finite n, but so if there's a bias at finite n, you have you get a variant of this inequality where this guy here, where this guy here involves further terms. So
Bias.
exactly. So as it stands here, it's something which is interesting in the large n limit, but you can get a variant which holds for finite n. But this is not because this guy here doesn't hold for finite n, it's because maximum likelihood is inconsistent for finite n. So rather the consistency is defined only in the large n limit.
Because the variance of theta hat goes to 0 with n, right?
Yes.
And so, but the product has to be larger than 1. So that means that the I has to increase with n.
Yes, which it does.
Oh, it is. Okay, fine. Thanks.
Okay. Do I have another 10 minutes to play you on this? And then we take a break and change the topic? Okay. Now you know about all the tools of frequentism. Let me set you a challenge. A single set of data which consists of 3 numbers, x1, x2, x3. 2 totally different quantities. One of them could be the temperature in Havana today. The other one could be, I don't know, the number of pieces of bread I had for breakfast, and I don't know, agricultural output in Sweden last year. And they have certain means. Call them theta 1, theta 2, theta 3. Let's make them Gaussian distributed. And then ask for the maximum likelihood. Estimate all the parameters theta, theta 1, theta 2, and theta 2, given the data x1, x2, x3. Now what would you say is the maximum likelihood estimate of this distribution? That's not yet the challenge. That's the, so you don't have to be worried about this. Well, it's not particularly hard. We would take the logarithm, sorry, it's here. Involves normalize properly. No, I'm jet lag. Okay. Variance 1. Okay. So distribution with its peaks centered around theta 1, theta 2, theta 3, and now we're trying to learn about these parameters. Any guesses on what the maximum likelihood estimate is going to be? We could just take the logarithm of this and maximize with respect to theta and do the mathematics.
Sorry, there is only one instance of every variable?
There's, in this particular case, one instance of every variable. But that doesn't really matter for this likelihood. It's, it could take...
It would be exactly the same value.
It'll be exactly the same values. It'll be theta 1 equals x1, theta 2 equals x2, and theta 3 equals x7. And that's the maximum likelihood estimate. So far, so uncontroversial. Now the question is, how good is this estimate? It simply says, I was given one number, I want to learn its mean. Can I do better than just assuming that the mean is this value in a systematic way, and for all values of theta 1, theta 2, theta 3? So can I find a function of x1, x2, x3, which I can maximize instead, and that gives me a better estimator for all values of theta than these guys here? And the question is that that exists. And I'd like to take a poll on whether you think we can do better than this estimator, which says, well, x1 is 7, and theta, well, we can't really say it's 8, we can't really say it's 6, so we just say it's 7. The question is, can we do better than this? And who would like to say, no, we can't? And who would like to say, yes, we can? Nobody says, yes, we can. You're not quite sure. You think maybe. Right. And the shocking thing is, everybody who put their hands up, including myself, is wrong. And there is a way to improve for all values of theta on the maximum likelihood estimate. And this was a shock to statistics. It was a shock in particular to frequentism, and frequentism hasn't quite recovered from this shock. And the statement is, yes? Better in the mean squared error sense. So if you repeated this, you would do systematically better under a mean squared quality measurement. Well, what I'm going to say is I will give you one which does better, and that is simply the shocking statement. The shocking statement. Well, we all said there's nothing better, almost. And the statement advanced by James Stein is James and Stein 1 minus 1 over x squared times x. So an estimate which says, let's take these three numbers, calculate their distance from the origin, take 1 minus the inverse of this distance squared, and use that as a p-factor on x. That performs better in the sense it has a smaller mean squared error than maximum likelihood. And, pardon? But it's not a consistent estimator. That is true. Yet it has and that's a very good point, yet it has a small mean squared error. So if you're willing to sacrifice consistency, you can get a better estimate, but you throw consistency out of the window. Yes?
So if I'm interested in estimating the agricultural output of Sweden, I do better by using the amount of bread you make.
Exactly. Absolutely. And this is what is so annoying about this. This is what really, really frightens statisticians. And I hear every statistician knows when she or he learned about this result. It's like the death of Kennedy or what have you. Apparently it's an event which is etched on every statistician's mind. It's a highly annoying result. And the key thing that these are three estimates, these are three numbers. That is important. And in two dimensions, with one number or two numbers, it doesn't work. But in dimensions 3 and above, it works. And it's actually a fairly stable result. You can play with this and it still holds. For instance, you can change the variance. And you can construct an estimator which is adapted to different variances and it still beats maximum likelihood. If you don't know the variance and you need to estimate it from the sample, you can also do this, and there's an estimator for this, which still beats maximum likelihood. Just two things, and then we'll come to the discussion. What James and Stein showed is that this estimator outperforms maximum likelihood. You can ask, are there better estimators than this one? And there is an even better one, also found by Stein, which says, if this here is negative, replace it by 0. So replace this here by the maximum of this number and 0. That still does better than the original James Stein estimator. And then you can ask, are there better estimators still? And you can prove the existence of even better estimators, but you can't construct them, or nobody has found ways of constructing them. Always by mean squared. If you measure quality, this is, pardon?
I don't see why this is a paradox.
Because
Essentially, you're saying that there is an estimator which is better according to another dimension. So it depends on the dimension
this is very true. This is very true. The key thing is, you give me another measure, I give you another estimator.
Exactly.
And but the mean squared measure is such a sort of natural thing to use that this was deeply shocking to frequentists. I would like to resolve the shock somewhat using the objection of Monet and saying, look, this here is biased. And in the limit of large n, so this is the estimator for n equal 1. If n gets larger and larger, this estimator also changes. You need to put n into it. And it gets progressively closer and closer and closer to the maximum likelihood estimate. So in the limit of large n, the paradox is actually resolved. There is no paradox. And I would like to tell the statisticians who are deeply shocked by this, statistics is only meant to work perfectly if the sample size is large. And all the problems you might have or might not have if the sample size is finite is something we need to live with. Still, I find the objection you had of saying you need to know how many bread rolls I had for breakfast in order to do a good estimate for the output of Sweden, I also find that disconcerting. And it's at the heart of why this is called the Stein paradox.
Well, it's not like that, right? Because if you were to want to, now if I want to estimate how many you had for breakfast,
yes,
in that case, I cannot use the Stein construction. It's only if I want to get the cumulative error on the sum of the three quantities, then I do better with the Stein.
Very true.
And that's playing actually the...
Absolutely.
Yeah. Yeah.
Yes.
And that resolves
Yes.
the paradoxes.
Yes.
Yeah.
So this is true only for the Gaussian model, or that's a more general?
You can play this with other models too, but get different estimates. Okay. So the second point of view, which is taken up in statistical inference, runs under the name of Bayesianism. And it's based on a very simple but profound theorem, first derived by Thomas Bayes 200 years ago, a good while back, and it's a statement about conditional probabilities. And the statement is the probability of a random variable theta conditioned on x is equal to the probability of x conditioned on theta times the probability of theta divided by the probability of x. And this is a theorem that is simple to derive if you look at a joint probability distribution and say, well, there's two ways of thinking about this joint probability distribution. One is to say, let's pick the random variable theta from a distribution and conditioned on the value of theta, let's pick x. Or go the other way around and first pick x and given x derive theta or generate theta. And if you set these two equal and divide by p of x, you get this result. Now, the power of this simple relationship between conditional probabilities in statistics comes from the interpretation of saying, well, let's make theta a parameter, a random variable. This is a relationship which holds for all random variables. And if we consider theta a random variable, then we can derive a probability distribution over theta given x, the data, from these quantities here. So this is where we need to deviate from the frequentist statement. Remember, frequentism said the parameter theta is unknown, but it's fixed. The truth is out there. We just don't know what it is. Instead, we now take a different point of view and say theta is a random variable. It gets drawn from a random distribution. Call it pure theta. And given theta, we can generate x. And these probabilities enter into the quantity we're after. That's what is the probability that theta takes on a particular value given we observe certain data. So let's return to the example with the biased coin. We want to know, given we have 15 times 8 out of 20, what is the probability that the coin is biased? So let's set theta equal to 1 if the coin is biased and equal to 0 if it is unbiased. This theorem here tells us exactly what the probability is that we have a biased coin. And that's a stupendous achievement for such a humble statement about joint and conditional probabilities. However, it comes at a cost. And it comes at the cost that beyond what we have here, remember that's the probability or the likelihood depending on which way you look at it. That's the model which generates x from the parameter theta. Beyond that, we also have a probability distribution over theta and a probability distribution over x. And the key novelty is that this quantity here, which doesn't even exist in the frequentist universe, it's so the probability distribution over theta. It has a name. P theta is called the prior distribution. And that's the quantity at which a frequentist looks at and says, I don't know even what this is. It makes no sense whatsoever. It only makes sense in the Bayesian approach to statistics. In the biased coin example, it comes from a whole ensemble of coins. Let's look at all the coins which are in use in this particular city. Most of them are unbiased, but maybe a few are biased. Pick one at random, and you have an unbiased coin with a certain probability and a biased coin with a certain probability. Put that in here, multiply with the conditional probability of x, and this will go some way of calculating p of theta given x. The second quantity entering is p of x given theta. That's the quantity we already know. And that's the quantity which a frequentist is happy with. It's, as a function of theta, what we meant before as the likelihood. P of x has a name. It's called the evidence. And if you need to calculate it, you can calculate it from the joint distribution of x and theta. Both of as first picking theta and then given theta picking x and summing over all theta. And this quantity here is what we're after. How probable is a particular value of theta? How probable is a biased coin or an unbiased one given the data? And it also has a name, it's called the posterior probability. Now, with this probability, we can now play. For instance, we could ask, given all the possible values of theta, which one is the most probable? Let's make theta a continuous valued variable. We have a whole probability distribution. And we can ask, what is the value of theta which maximizes the probability? Or we can calculate observables. We can calculate the mean value of theta under this probability distribution. There's one technical difficulty, and this led to Bayesian methods being, well, living a somewhat quiet life until 1 or 2 decades ago, and that's this sum here. Suppose that there's many parameters to estimate, and they come from a large space. Say they can take on many different values. And there's many of these parameters, so this sum, or this continuous value variable theta, this integral, is a high-dimensional sum or a high-dimensional integral. And until computers became as powerful as they are today, this sum was simply hard to calculate in practice. So Bayesian methods were thought to be, yes, they exist, but they need this awkward prior here, and we don't want to think about it. but also they're practically hard to use because we don't know how to calculate P of x with the number of parameters and so on. Mind you, the situation isn't so bad if we're only interested in the value of theta which maximizes Zs posterior. Then, for instance, this P of x is just a constant, and we can maximize the quantity up here in the numerator over theta and say, well, this is a constant which in practice we can't calculate, and but the value of theta which maximizes Zs probability, that's something we can calculate. In this particular context, if P of theta is flat and the probability of one particular value of theta is the same as any other, the probability over theta isn't peaked in some way, it's simply a flat distribution over a finite number of possible states of theta, well, then this here is also just a constant of proportionality, and what we're left maximizing is the likelihood. So for the particular case of a flat prior distribution, maximizing the posterior probability and maximizing the likelihood is the same thing. And I would view this as a justification for the maximum likelihood estimate through the back door of Bayesianism. Now, Bayesianism enjoyed a revival driven, well, first of all, by the advent of task computers, and it also attracted a lot of interest from statistical physicists who said, look, this sort of thing is something we know how to deal with. We can view this as a partition function. If the likelihood is an exponential function, and then we can use methods from statistical physics in order to calculate this. And this, in part, is what brought us here today via the link between inference, in particular Bayesian inference, and statistical physics. I'm not going to say much more about Bayesian methods, except that this basic idea has been varied in a huge range of different ways. For instance, the prior distribution might itself depend on a parameter. And this parameter can again have a prior. And this prior distribution might again have a parameter with its own prior, and so on, and so on, and so on, leading to what is called a hierarchical Bayesian model. Or the priors of different parameters might not be independent, but might statistically be linked. So the corresponding probability distribution doesn't factorize. And this leads to what is called Bayesian networks. Also, if you want to calculate this here, there's a huge range of approximations which look very similar to, or which in many cases look very similar to approximations we're used to in statistical physics. And one of them is what essentially is Monte Carlo estimates. You know Monte Carlo estimates in order to, or statistical physicists among you know Monte Carlo estimates in order to calculate expectation values under a probability distribution which is hard to treat fully, and instead you sample randomly from it. And the same approach can be taken to this particular sum over theta, and it's called approximate Bayesian computation, or conveniently ABC. And with this, I would like to close what I have to say about Bayesianism and illustrate the two and the distinction between them using one particular image. comes from a webcomic called XKCD. I see some smiles, so some of you know it. They say it's a webcomic on love, sarcasm, and science, I think. And it uses very simple stick figures in order to make incredibly profound statements about love, sarcasm, the nature of computation and mathematics. I'm a big fan of it. And in this particular case, the debate between frequentism and Bayesianism is illustrated in the best possible way, I think. But I urge you to explore this comic because it can serve as a guide towards life in general, not just love and sarcasm. So check it out.
Can you read it?
I'll read it.
Can you put that on my computer?
I can't take the other.
But it just worked.
It comes and goes.
Oh, it comes and goes. Okay.
My hand
You have to read it fast. I can do this one. There it is.
Okay. That's good. Okay. So, this is about frequentists and Bayesians. And what we have is the big question, did the sun just explode? It's night, so we're turned away from the sun, and we can't tell, can't observe the sun. But what we can measure is a neutrino flux through the Earth. So we have a neutrino detector, and this neutrino detector measures whether the sun has just turned into a supernova, which is of course a very important question to check. After, and it works like this, it measures the neutrino flux in order to figure out whether the sun has become a supernova. Then it rolls 2 dice. If they both come up 6, it lies to us and gives a false reading. Otherwise, if not both of them come out 6, it tells us the truth. So here's the machine. Let's try. Detector, question, has the sun turned into a supernova? Rolls the dice and says, yes. Now, the frequency statistician says the probability of this result happening by chance under a boring null model, that the sun hasn't gone supernova, that's a boring null model, is 1 in 36 or I can't even read it, 0.027. That makes about sense. About 3%. Since 3% is less than 5%, remember the magic p-value cutoff, I conclude that I must reject the boring null hypothesis and conclude that the sun has turned into a supernova. The Bayesian statistician says, I'll bet you $50 it hasn't. And this to me sums up exactly the strength, the relative strengths and weaknesses of these two approaches. The frequentist uses no information beyond the elementary statistical model P of x given theta.
So are you saying that the Bayesian, the morale is that the Bayesian relies on the prior and completely ignores the data?
And the Bayesian says, look, there's more to it. I use information on the probability that the sun has gone supernova in a particular instance. And what a frequentist implicitly does, if things are being done right, is to adjust the p-value. This p-value cutoff of 5% simply makes no sense in this experiment. If you apply it, you get a result which makes anybody laugh. The Bayesian statistician says, I use information from outside the roll the dice experiment. I don't know how to generate this. I can't fix a probability I can't assign a probability to the sun having gone supernova at a particular moment in time. But whatever it is so small that if I multiply it with the likelihood of the probability of the sun having gone supernova, given the machine tells us so, is very, very small.
So the morale is
Yes.
that the Bayesian method is as good as its prior.
Absolutely.
I mean, that's
Absolutely.
the conclusion, right?
Absolutely. But that's one conclusion. And the other conclusion is, while this is true, the same information enters frequentism by the back door via the cutoff. The right cutoff for this experiment shouldn't be 5%. It should be 0.00000 and so on. Something which quantifies the probability of the sun actually having gone supernova. So the Bayesian, so the morale is also, Bayesianism makes an assumption which the frequentists hate, but at least everything is on the table. All the assumptions are in the open. You have to make them, whether you like it or not. They're in there, for instance, via this cutoff, and if you fix the cutoff by convention and say, well, 0.05 is the magic p-value, then...
But I mean, the cutoff of the frequencies is also on the table in a sense, right?
This is true, but it's often fixed by convention, and in this particular case, it simply makes no sense. Both are, so don't knock, I would say don't knock either. This comic puts the juxtaposition sort of very, very clearly and says both of them have assumptions. This assumption here is a probability distribution over the prior, and this here, which you need to choose, and this here is an appropriate cutoff for the p-value, which you also need to choose. So in the end, you don't, the two approaches, even though its proponents are frequently passionately opposed to each other, both of them have the same intrinsic problems. Yes?
So I have kind of a comment question to you. The main thing is that you assume evasion is a joint probability of the parameters and data, as you explained, elucidated. When is that not a reasonable model of the real world? Let's say you do a bio experiment, and when you set the parameters to something, you're destroying the cells or whatever you do, and then you're not allowed to do, you cannot on the same data do another set the parameters to something else. And then it might not be a good idea that you actually base such a joint probability.
Yes. And this would be one of the objections of a frequentist to the Bayesian approach, and say, look, this quantity simply makes no sense.
I would say it's a joint probability.
Pardon?
I would say it's a joint probability sometimes.
Well, it's the picture is
Sometimes.
the picture is one of many worlds. So there's one world in which you do the experiment with this parameter value, and there's another world in which you do it with another parameter value, and P or theta is unsolvable over the different worlds. And that may or may not be a good model for reality.
What I'm asking for is, I mean, we know that frequentism has kind of a dominating position, at least in medical research, right?
Yes.
Yeah. So is that related to this fact that in medical sense, you actually don't believe in this joint probability?
Right. I think the reason it's dominated, the medical world and many others, is that the Bayesian distributions were impossible to calculate in practice, and with p-values, everybody had a way of calculating something they could write down and compare.
I think that the reason in the medical, that the medical people, they don't want to publish results which depend on the prior. They don't.
Yes, and instead,
they know, I say, they want to say, I have cancer, under my prior, there's cancer in this day.
Yes.
I mean, they don't want to say that.
That is very true, and instead they publish results which depend on the p-value, and they always cluster very neatly just below the p-value they need in order to publish, which is an sort of internal embarrassment. PhD students can be advised by their supervisor to produce result-oriented statistics and look for tests which produce a p-value below 5%. So I know of one particular case where a student came to me and said, look, my supervisor wants me to try out all the different tests I can run on this data and look for one which makes it statistically significant so we can publish. But I think this is wrong, and what should I do? And there isn't much you can do. Pardon? Except change fields, yes. In fact, this particular person dropped out of science. I also happen to be married to her, so it's a personal connection. Okay, so with this particular, thanks a lot for your questions.
So there's the other thing, Johannes, is about this Bayesian that you say that the Bayesians assume that theta is a random variable. Actually, I don't really agree with that statement. I think, the way I like to see this Bayesian story is that the Bayesians, they think there is a fixed parameter theta out there, but they don't know that parameter. And they quantify, so it's a subjective story in which they quantify their uncertainty in terms of a prior. And so it's not a many-world story, it's a one-world story, but it's a subjective story.
I fully agree. This is, if you combine Bayesian statistics with a Bayesian view of what probability is, this is what you end up with. Yeah. I totally agree. But I don't think you have to take this step.
It doesn't matter.
It doesn't, exactly, it doesn't matter. It draws its name. It's called, the two are linked via the name Bayesian interpretation of probability. But you can be a Bayesian and take a frequentist probability, a frequentist view on probability. So you can do Bayesian inference, but use frequentism to interpret probabilities. And then you end up with a sort of many world picture. Or I think you could also be a Bayesian in your view on probability and say it quantifies ignorance or knowledge, and use frequentist tools for inference. Historically, these were linked, but I don't think there's a reason for tying one together. Okay, and with this, I would like to turn about and apply them to a particular model and try to infer the parameters of this model. And this model runs in statistical physics under the name of the Ising model. In statistics, it has a whole range of names. It's simply a probability distribution over binary variables, which can be 0 and 1 if you're doing information theory. It could be plus or minus 1 if you think about little magnets, but it's simply variables which are binary, yes or no, plus and minus 1, 0 and 1, and which are statistically linked with each other. I'm going to stick to the physics name and notation. So I'm going to call it the Ising model, which draws its name from a set of spins. I draw them here in 2 dimensions, but it could be any dimensionality, and each spin is a variable which can be plus or minus 1, and these are linked with interactions which cause correlations. And these interactions mean if this variable here points up, this here likes to point up, or maybe it likes to point down. The first would be a positive interaction, and the second one a negative one. And this first came up as a model of magnetism in the 1920s. In a one-dimensional chain of such spins with only positive interactions, it was studied as the PhD thesis of a young PhD student named Ernst Ising. It was suggested by his mentor Lenz in Göttingen, and he solved this model and was hoping to find a phase transition. He was hoping to find a high temperature phase where the spins all point up and down, and the low temperature phase where they like to point in the same direction. He didn't find that and was very disappointed and thought that, well, maybe magnetism has some other origin and it can't be reduced to such simple binary variables. Maybe it's a quantum mechanical effect that needs quantum mechanics in these variables. But it turned out that the lack of a phase transition simply came from the dimensionality. And if you move to 2 dimensions, so if you arrange the spins in a 2-dimensional lattice with positive nearest neighbor interactions, that there is, in fact, a phase transition. It took 20 years and the genius of Lars Onsager to work that out, by the time of which, by the way, Ernst Ising had been forced to leave his teaching position in Germany because of the racial Nuremberg laws under the Nazis. Ernst Ising happened to be Jewish. He was forced to leave the country, and luckily he managed to emigrate to the United States and became a teacher there. And because of the chaos in the Second World War, he wasn't even aware that his PhD thesis had started to attract intense interest from mathematical physicists. And it wasn't until the end of the war that he learned that his model had become famous in physics. He then moved to university teaching and lived until the late 90s, and grew to see his model become the basis for explaining magnetism and many things besides in statistical physics. So, what is a Lianchin model? It's a probability distribution over spin variables, binary numbers, plus or minus 1. I call the first one S1, the second one S2, the third one S3. Arrange them like a vector denoted S underscore. And this model depends on some parameters. first write it down and then talk about it. So this is the probability distribution over the spin variables given parameters j and h, and it's simply an exponential distribution e to the sum function of spins and parameters divided by a normalization constant that has a name, it's called z traditionally, which makes this distribution normalized. And the magic function h inside the exponent here takes the spin variables and calculates how many of those point in the same direction of these h parameters. You can think of these as magnetic fields. If many spins point in the same direction as the fields, you get a large negative number here, and that would produce a big probability here. So this term here tends to align the spins with the h variables. So if h1 is positive, more often than not, Si will point in the positive direction rather than the negative one. And if h is negative, more often than not, it'll point in the down direction. If you make h1 minus infinity, then the probability of this spin pointing up will get lower and lower the more you make this large and negative. And these terms here, they introduce correlations between spins. So if j, for instance, j12 is positive, then if spin 1 and spin 2 point in the same direction, this will give a positive contribution. Together with these two minus signs, it'll make the probability of S1 and S2 pointing in the same direction larger than the probability that they point in different directions. So it's a statistical model over spin variables which is inspired by magnetism. You can think of these parameters here as magnetic fields and these parameters here as physical interactions between spin variables. But from a statistical point of view, this is simply a parameterization of a probability distribution which encodes only a certain propensity to point up or down for each variable and a certain propensity for the variables to be correlated or anti-correlated. And as such, it's the simplest model or the simplest non-trivial model of binary variables. It's the simplest model which has pairwise correlations between the different variables. And what we want to do now is, given somebody gives us data on these spin variables, what we want to do is we want to calculate the values of these parameters. So the classical inference problem. So the data is spin configuration, sample many times. Let let's label these times S1, S2, and so on up to Sn. And the task is let's infer the parameters of the model, namely the matrix of interactions and the field parameters. This is a model, as I said, it's inspired by magnetism and statistical physics, but it's been used over the last 20 years in contexts far outside statistical physics, for instance, to model the activity of neural networks. So we measure how frequently a particular neuron fires, and we try to learn something about or we measure how sets of neurons fire, and some of them are correlated, some of them are anti-correlated, and we want to learn the parameters of a probability distribution parameterizing these correlations. Another application which you'll probably hear about and which has been pioneered by Martin Berg is the use of a model just like this one here to model the statistics of amino acids in proteins, and what we're trying to learn is what are the particular shapes these proteins fold. But for now, we'll simply consider the technical problem and of inferring these parameters of this particular probability distribution. How do we do this? Well, we start with maximum likelihood, either because we're frequentists or because we're Bayesians and we think there's nothing to decide particular values for these J's and H's, so we assume that whatever prior we're dealing with, it's flat, and as a result, what we're trying to maximize is the likelihood. So the next step is to write down the likelihood function as a function of these parameters given the data, and ask what it looks like. Yeah, can you just take me 5 minutes? Perfect. Very sweet. Let's take the logarithm of a likelihood. The logarithm because it'll make the analysis a little bit more convenient, and it doesn't change the position of the maximum. Because the log is a k function, the maximum of the likelihood is going to be in the same position as the maxima of its logarithm. And I wish I hadn't erased the probability distribution here, but if you just think back or look back at your notes, it was an exponential probability distribution. So taking the logarithm is going to give us a particularly simple form. So the quantity to maximize is this quantity here. It consists of two terms. sum over the matrix of couplings times the correlations we observe between spins with a sum over all the different samples. We assume that samples are identically and independently distributed, so the probability distribution is a product over all these different samples, and the logarithm of this function here is a sum over the different samples. And if we give these guys here names and call the sum over all samples of Si, Sj for these different samples, call that C, it's a correlation, and for 1 over m sum over mu S mu. We can think of this as a magnetization. How often is spin I up versus how often is it down in these samples? Then what we have here is m times Jij, Cij plus sum over I with m0 mi minus m times log z j and h. And there's two interesting things about this. First, all terms now linearly depend, or explicitly depend linearly on the number of samples. So it's a quantity which is extensive in the number of samples. The larger the number of samples, the bigger this logarithm is going to be. And it depends on the data only via two particular quantities. All you need to know about the data is the matrix of correlations and the vector of what in physics one would call magnetization. So you only need to know how strongly correlated are two spins or two variables, and how often is a particular spin up versus how often is it down. Anything else does not matter. So in order to calculate this, you don't need to know the full set of observations, but you can boil down these observations to the correlations of pairs of variables and the frequency with which a particular variable is up or down. For instance, we don't need to know anything about 3-point correlations or 4-point correlations in order to calculate this likelihood and in order to maximize it. This result is going to be useful and a dead end later on, and what we're going to do tomorrow is we'll discuss various ways of maximizing this likelihood, which turns out to be hard because, not because these guys are hard to deal with, that is easy, you can estimate the J's from the data, and these are the C's from the data and the M's, and these are just parameters which we try to maximize. The hard term will turn out to be this particular case, this particular function. It's a partition function which involves a sum over all the spin configurations, and we're going to discuss different ways of dealing with this term, and we're going to discuss one particular way which entirely sidesteps the issue of calculating this term here. And all of that is going to be in my third lecture tomorrow, I think it's the second or third lecture in the morning, and I look forward to seeing you there. That's it for me.